Now, ladies and gentlemen, the fourth and the last keynote speaker for today is Prof. Dr. Ridza Wahiuddin, Deputy Director Research and Innovation, International Islamic University, Malaysia. Dr. Ridza obtained his BSc, MSc and PhD degree from University of Manchester Institute of Science and Technology, UK in physics. For his outstanding pioneering work in quantum optics in Malaysia, he is the recipient of the 1994 National Young Scientist Award by the Malaysian Ministry of Science and Technology. So, the University of Manchester awarded him with the highest doctorate degree, Doctor of Science, for his work in quantum optics. So with this, I would like to take on to the Prof. Ridza.
Bismillahirrahmanirrahim. The session chairman, Professor Nisa Ahmad Sadiqi, Director Sukkur, IBA, distinguished guests, brothers, sisters, Assalamu alaikum warahmatullahi wabarakatuh. So, when I was coming here, I was on this flight. I had a choice because I had some time to view the movies. So there were a variety of movies available, but somehow I made a choice. I wanted to see what are the traits, characteristics of someone by the name of Ramanujan. So he actually went through a lot of trouble, and he's famous for his partitions and combinatorics, and he actually was invited to Cambridge, and he had difficulty to get admitted as a FRS, even as a fellow of the college back in Cambridge. The essence of what I'm trying to tell you here is not just about how this great man was able to do some, kind of contributions to mankind. But along the way, there was this clash of belief systems. His supervisor, Hadi, was a staunch atheist. Ramanujan is a strong Hindu. So he always had this clash with his supervisor, Hadi, because Hadi is always pushing for proofs. But he actually came from the point of intuition, relating everything, what he discovered, to divine or divinity. On the other hand, his supervisor is saying, I don't want to see all this intuition, I want to see proof. So to cut the story short, when he actually died at the young age of 32 because of TB, his supervisor actually admitted in his obituary that this wonderful personality actually made a lot of contributions and is waiting there for us to discover. There's a difference between discovery and creating. So we need to have that understanding, because whenever we actually embark on an activity, research, for example, the end should be clear to us. Harnessing the vacuum for quantum computing. For what? When we talk about being human beings, because I started off by talking about belief systems, there's a difference between being human beings and human doings. You may be hearing me, but you are not listening. I may be communicating, or I may be talking. The students here may be studying, but they are not learning. But when the Prophet ﷺ taught us, there is something very dear in our body that dictates everything else. And that is the heart, the spiritual heart. But many of us may have lost sight that it's more of this that is controlling everything. That's why when we actually look at things like Ramanujan and all these things, there's a connection between being a human being and not just be a human doing. To actually have that connection between your mind and your heart. So the clarity of the journey, of the aim, of why you want to do something is very critical. Let me cite you a very simple example. Rizvi al-Jabbar. What was his intention when he was embarking on algebra? He was trying to solve that very important question of inheritance. The question of inheritance was pertinent, and we are now enjoying all what he has done along that line. So the clarity of vision, clarity of answering questions, problem statements, those are the things that drive great discoverers, great scholars of the past as well as future and the present. All right. I wouldn't want to digress further about my topic. A brief outline of what I'm going to talk about, 4 bullet points. First one is understanding the vacuum. If you Google vacuum, what will you see? Most probably a vacuum cleaner. So that's not what my topic is all about. I'm going to talk about vacuum. Secondly, a bit of quantum computing. Quantum computing and the vacuum, and some conclusions. Now, I'm not sure whether you can see it, but just to highlight, if you look into the definition of vacuum in the Oxford dictionaries, and all you have is something about nothingness. There's nothing there. After actually you suck up all the particles, there seems to be nothing there in that space. So that is the understanding of the normal person, the layman. A vacuum is something that is associated with nothingness. But then again, if we look at, in reality, when we have actually sucked out all the particles and lowered down the temperature to, say, absolute zero, then if you look into this, you see, let's say these are the dots representing the particles. Eventually, what we have, even the radiation becomes grounded at the lowest energy. So which means, in spite of nothing that's there, there is still something there. Which is that kind of fluctuations. Okay? This kind of vacuum fluctuations is a result of what we say as something that is quantized, for those people who want to talk about quantization. So the mathematical model associated with quantizing matter, or in this case radiation, you actually, to make it simple, associate with every single mode of electromagnetic radiation with a quantum harmonic oscillator. Right? For those who are familiar with harmonic oscillators, then you will realize that if you look at this equation here, the energy for the oscillator, this n, an integer, will reflect the energy level of the oscillator. So if you associate an oscillator with each mode of the EM field, then the more energy it has, it will climb up the ladder. For classical explanation of oscillators, they do not have all this discreteness. It's actually a continuum. But for quantum harmonic oscillator, the energy is discretized, and it's actually represented with n equals to 1, 2, 3, 4, 5. And the more energy you have, it will climb up the energy level. Now, what happened when n equals to 0? So when n equals to 0, interestingly, you will see that you have this half. That half, Planck constant omega, frequency of the mode, is always there, even when there is no photons, we call it. When n equals to 0, there are no photons. But you still have this half H cross omega, which corresponds to the 0-point energy. So this is a problem until today. Okay? Physicists, mathematicians try to solve this. Because you can imagine, as we've seen just now, by removing all the particles and lower down the temperature to near absolute zero, in reality, you still have these fluctuations. These fluctuations come from this 0-point energy. So if you imagine every mode is there with 0-point energy, there is an infinite amount of energy out there. So the way to handle this 0-point energy, because of this infinity problem, is something analogous to how we deal with potential energy. Simple analogy. If you want to measure the potential energy of an object, we need to have a reference. And what actually we measure is the potential difference. So a similar argument for this, the physicists call it renormalization. But actually, in actual fact, you are fitting the problem with the couple. So it's still an active research until today. How do you actually cater or address issues when you talk about this infinite energy in the form of 0-point energy? So what I've done so far is try to convince you nothingness doesn't mean there's nothing there. There's something there in the form of energy. Now, when we talk about in the form of energy, we need some kind of evidence to show that it exists. So this is a famous thing that associated with vacuum is the Casimir effect, the word discovered by Casimir, the Dutch scientist. So what happened was, if you are able to bring in two mirrors, okay, and then you put it very close together, right? Just like if you bring two pieces of paper and then you blow in between the two papers, the two papers will get attracted. Why? Because by blowing in between the two papers, you basically have reduced the pressure, right, in between the two papers, and the outside pressure will push the two papers to be attracted or collapse to each other. So, similar manner, when we talk about Casimir effect, Casimir force, the idea is the existence of the 0-point energy or these fluctuations cause the pressure to drop in between the plates or the mirrors. So because of that, then we see that this effect do exist and it has been proven experimentally. So there's another analogy. When two ships are nearby, they will sort of be drawn together, attracted, to explain this Casimir effect. Now, the question here is, we look at the vacuum or the quantum vacuum from the perspective of something that may be negative. Why do I say that it may be looked from a perspective of negative? Because we have a question here. If we look at this slide, the question is, how long can a quantum state live? So the challenge to the scientists, the physicists, the mathematicians are, how can you actually sustain a quantum state for a longer time? Right? So that is what we say as the coherence time. Now, the simplest thing, or the simplest example I would like to share with you, here where you have damping, or we say that there is energy loss. So if you take an electron in a two-level system, and you excite this electron in the upper state, by right, it's supposed to be there forever. But why is there a jump from the upper state to the lower state? What is the explanation? So, if you dissociate yourself from religion, different people will give a different answer. Universally, you will be able to answer the same in terms of the how and the what. Right? For Newton, for example, when he discovered about something that is causing the apple to fall down due to gravity. That is the why. Is it the why? Is it the how? Is the what? But for Muslim scientists, it will go beyond. Why does the apple, drop? You have an answer to that. You go beyond. Because you can answer that there is a reason why that thing fell. Okay? So here, again, when scientists were looking at this, why is this electron suddenly, randomly, apparently, jumping from the upper state to the lower state? So the answer is because it is interacting with the vacuum. The vacuum, as we've seen just now, contains this zero-point energy which are causing the fluctuations. The fluctuations in turn interact with the excited electron and causes it to dissipate. It is damped by a reservoir and then it's de-excited. So it jumps from the upper state to the lower state. And this is what Einstein attributed as spontaneous emission. Okay? So spontaneous emission is an example where you have the vacuum causing a quantum state, a simple example here, it will dissipate. It doesn't stay in the excited state forever. There is a reason why. Now the question that the physicists, the scientists can answer is, why at that particular time it jumps? For Muslims, maybe we can answer. But some other people may have difficulty to answer. Why does that electron jump, let's say, 10 or minus 6 seconds? Why it doesn't jump earlier? Why? They cannot answer that. There are some problems that we have to acknowledge. That's why I believe, especially in the conference, we need to realize, first of all, to be aware that when we actually embark on a research or whatever we are doing, we need to understand that we have resources within ourselves. We cannot forget that part of our body where we need to harness, optimize the resources that God has given us and see the whole problem holistically, comprehensively. Now, when we look at the example of spontaneous emission, you see, if you do this experiment, you excite the electron up there many, many times. You can do this two ways. Either you use the same atom with the electron, excite, de-excite, and you collect the data. Or you have an ensemble of two-level atoms, all together excited, and let them de-excite over time. So either way, you will see that you will get this behavior. Over time, there is a decay in terms of the population. If you take the average population of the two-level atom over time. So what it means is, just like you have the analogy of having a swing, you're pushing the swing with your little brother or sister. If you do not actually supply energy, the amplitude of the swing will be damped. Eventually, it gets to zero energy. So that's what actually is happening as far as spontaneous emission. So I started by talking about this example when I said that we may look at it as something negative. Negative here simply because of the existence of this damping, which is due to quantum fluctuations, we may not be able to sustain an excited two-level atom for a longer time. So it is the culprit that is causing the excited atom to decay. So from that point of view, we say it is a problem. It is a negative aspect. Now, if we are in the business of building a quantum computer to become somebody who has a solution, we start to ask, can the problem be the solution? Sometimes we forget that the problem is always a problem, and we try to tackle it as an enemy. But being a scientist, you always have the option to say, can the problem be the solution? So, ASIT, A-S-I-T, is a simplified version of TRIZ, T-R-I-Z. This was actually introduced a couple of years back by this Russian, about 40 odd tools on how to get an answer if you have a certain problem. So Ronnie Horowitz simplified the TRIZ tools to about 5. Okay, so you have 5 tools instead of 40 to actually answer some of your most important research questions. So number 1 is, they call it the multiplication tool. So I'll go through at least 2 to highlight how useful this tool is. But if you look at this slide, what I'm trying to say is, if you go further away from the bullseye, not the bullshit, but the bullseye, if you go away further, if your solution is away spiraling out, then it is costly. So your solution ideally should be near your problem. Right? If you have the oil spill near Mexico last time, the end result, the solution, what was it? Just plug. Put a plug onto what is actually leaking at the bottom of the ocean. So whatever other things more costly, it would be more dollars and cents. So look at the problem closely, and perhaps the problem is your solution. So here, if we look at the multiplication tool, for example, the Japanese had problems. After many, many years, they cannot do any more fishing near the shore. So they have to go deep fishing. So to catch these fish away, they have to travel, what, 1 week, 2 weeks, and then they have to bring whatever they caught back.